Okay, hello everyone. I hope you're all doing fine. I'm Rana Ahmed Sayed. I'm a teaching assistant at the German University in Cairo, as well as a PhD candidate at Helwan University. I specialize in solid-state physics, and today I'll be sharing my research about bismuth iron oxide, temperature-dependent electrodensity, and crystallographic study in correlation with magnetic phase transitions. So let's start by an overview. Okay. Let's start by an overview of today's presentation. First, I will give a brief introduction about perovskite, bismuth ferrite, and electron density map. Then, I will explain my methodology as well as share my results. Then I will wrap it all up in the conclusion. First, what is the crystal structure of a perovskite? Perovskite has the general formula AbO3, where A and B are cations and oxygen, or O, is an anion. A and B can be either of these given elements, but for this research, bismuth was chosen as A and iron was chosen as cation B, making the bismuth iron oxide, or BiFeO, with the rhombohedral structure in the R3C space group with this given unit cell. But why use perovskite? Simply because perovskite is a multidisciplinary functional material. Just by changing the spin or the charge or the orbital arrangement, its function can change, such as insulating to superconducting, ferroelectric, ferromagnetic. And in this study, bismuth iron oxide was chosen as a multiferroic material. But why bismuth iron oxide, or BiFeO? In the past years, bismuth iron oxide has attracted a lot of attention due to its unique properties, such as its being a multiferroic, its high Néel temperature and Curie temperature, its band gap, as well as crystal structure. Also, due to its applications in transformers and generators, the magnetoelectric effect in the bismuth iron oxide can be used in data storage. Also, BiFeO is a photocatalyst that can be used in environmental remediations, as well as an active layer in solar cells. What's an electron density map? An electron density map is a 3D representation of atoms in real space. But why do we need it? We need an electron density map to study the crystal structure as well as the properties of the material. It can be represented as contour lines, where the contour line represents regions of equal electron density. The various lines, or the various colors of the lines, represent regions of high electron density or low electron density according to a color-coded chart. This here is a representative example of the electron density map for our chosen perovskite, which is bismuth iron oxide at 300 Kelvin, from the ZX plane. The regions of high electron density map indicated here and here are the positions of the atoms bismuth, iron, and oxygen. But how can we construct this electron density map? Well, it starts with an X-ray diffraction to get the 2 theta and the intensity. Then the 2 theta and intensity, or the X-ray diffraction data, are then refined using any program based on Rietveld refinement. In this study, I used Full-Prof program. From this refinement, the unit cell parameters were obtained and the unit cell was plotted. The observed structure factor is obtained, as well as the calculated phases. Then, the obtained data are then processed using the Fourier transform or using the G-Fourier program, which is also a part of the Full-Prof suite of programs. G-Fourier program uses a fast Fourier transform to calculate the electron density based on this equation, where the rho of R is the electron density in electron per cubic meter, V is the volume of the unit cell, H is the reciprocal lattice vector, and f of H is the complex Fourier coefficient, and last R is the position vector. Then the program constructs the electron density map to visualize the atoms. Like I said, this program is also part of the foolproof suite of programs. Now let's move on to the methodology and results. X-ray data was collected at various temperatures from 300 Kelvin to 850 Kelvin using silver radiation at Max Planck Institute for Solid-State Research. Then, from this collected data, we can see that, and when compared with the standard card for the BiFeO, that the bismuth iron oxide exhibits a rhombohedral crystal structure in the R3C space group. Also, in the whole temperature range, no crystallographic transitions were observed. Only a slight peak shift, which is shown in the inset here, a slight peak shift towards lower theta is observed, which happens due to the thermal expansion with increasing temperature. Then, the X-ray data was refined using foolproof program, and here is a representative example of the refinement, where the red color represents the observed or the measured data, while the black color represents the calculated data, and blue is the difference between them. Also, Bragg peak positions is indicated with the green marks. This refinement was performed for all the temperature data, where we obtained the lattice parameters, which was then plotted with temperature. As previously mentioned, from the slight shift in the peak position due to thermal expansion, this was reflected in the increase of the values of the lattice parameters A and C with temperature that happens due to thermal expansion. Also, from the refined data, the unit cell was constructed at various temperatures within the measured temperature range. Then, for the electron density map, electron density maps were generated using the G-Fourier program at different temperatures, where different planes were scanned, and the detected atoms are shown in the plot in each plane. Here we have the XY plane. The bismuth atom is shown at different temperatures. YZ plane, the three atoms, bismuth, iron, and oxygen, are shown at several temperatures. The same happens for the ZX plane, where we also have the three atoms, bismuth, iron, and oxygen. Then, from the electron density map from the ZX plane, the electron density is retained for the at these given atomic positions. From the electron from the electron density values plots with temperature, we can see that there is an anomalous behavior near 600 to 800 Kelvin here, which is highlighted in the plots. This anomalous behavior especially for the iron and the oxygen atoms may suggest some sort of magnetic phase transition in the material around the 600 Kelvin. This was confirmed by a magnetic properties study where magnetic hysteresis loop and magnetization temperature data was collected within the same temperature range from 300 to 850 Kelvin. The data then, the hysteresis loop data then was used to calculate the susceptibility. This, of course, was collected using the VSM squid at the Max Planck Institute for Intelligent Systems. Then the susceptibility was calculated and plotted with temperature. Here we can see from the susceptibility plot and the magnetization plot that below about 650 Kelvin, the behavior of the susceptibility and magnetization is different or varies from above that temperature, which suggests that, or which indicates that below that temperature, iron oxide, bismuth iron oxide behaves as an anti-ferromagnetic material. Then, after 650 Kelvin, there is a rapid or a sharp incline or decrease in susceptibility and magnetization, which indicates a magnetic transition from antiferromagnetic to paramagnetic state due to the rearrangement of magnetic domains. Well, to summarize this, we can say that X-ray diffractograms showed that BiFeO adopts a rhombohedral R3C space group with no crystallographic transitions in the whole temperature range, but slight shift in peaks due to the thermal expansion, which was then reflected in the lattice parameters. But interestingly, an anomalous change was observed in the electron density of iron and oxygen around the region of the Neal temperature, suggesting that there is a magnetic transition happening to the BiFeO between 600 and 800 Kelvin, which was then confirmed by the magnetic study that showed that below the 650 Kelvin, there was a significant magnetization due to the antiferromagnetic order, but at the Neal temperature and above that temperature, there's a sharp decline in the magnetization and susceptibility as the material changes from antiferromagnetic to paramagnetic. In conclusion, we can say that X-ray data and electron density map can provide a preliminary insight into the magnetic transitions. And X-ray data measurement methods are not only cost-effective, but they also require fewer resources compared to the traditional experimental magnetic measurements. Thank you for your attention.
Thank you very much. Very interesting talk. We are a bit short on time, so if there is a very quick question, please ask. Otherwise, we just move to the next talk.
Okay.
Sylvia, I need to ask a question. Yeah.
Please go ahead, a quick one.
Yeah, actually, thank you first for your nice talk. I was wondering about Nel temperatures that you measured. Do you think you can control Nel temperature and shift it a little to higher temperatures than it is right now?
Well, that might happen by doping the material.
Yeah.
But with this state, or with this pure bismuth iron oxide state, and at least with these conditions, I don't think I can change or control the Neal temperature.
Yeah, that's why I just need your comment. Is it like doping? What kind of material, or what is like dopant element that you can do, and then you think that you can be able to shift the Nel temperature to higher temperature?
Well, I didn't try actually doping it, but I read in other research that they try using chromium as a substitute or as a dopant. I don't know what other elements we can use because, like I said, I didn't actually work on the doping part. I just worked with the pure BiFeO. But materials such as chromium and similar materials, maybe they can be used to shift the Neal transition temperature or other elements.
Okay, thank you. It's clear now.
Thank you.
Okay, sorry, we cannot take any more questions right now because we are running out of time. But please hang on in Gather Town so people can reach you there and answer the next further questions.
Sure, thank you.
Okay, so